Hello, ladies and gentlemen. We're going to be talking about acids and bases this week. Today, we're going to be talking about properties of acids and bases. We're going to look at the different types of definitions of acids and bases, dealing with Arrhenius and Bronsted-Lowry types. So let's go ahead and get started. Acids. Most of you know that acids taste sour. Things like citrus fruits have citric acid in them, and they tend to taste very sour. Lemons, grapefruits, things like that. Bases, on the other hand, taste bitter. Things like spinach or Brussels sprouts or cabbage have a bitter taste to them because they're alkaline or basic in nature. If you've ever gotten in trouble and had soap put in your mouth before, that soap would also taste very bitter because soap is also a base. Acids burn. We mostly know that already. We say that they are caustic. The stronger the acid, the more the burn is going to be. If you've ever cut yourself and got like lemon juice in there before, or lemon juice in your eye, you could tell that that acid burns. Bases are also caustic. They also burn. The stronger the base, the worse the burn's going to be. Things that have very strong bases like drain cleaners can burn your hands very, very badly. You have to wear gloves or be very cautious when you're working with very strong bases like that. Acids, we don't really write anything for how acids feel. Bases, however, have the distinct property of feeling slippery. Things, again, like soap are weak bases, and as you know, those feel very slippery. Acids react with metals to form hydrogen gas. So mixing an acid with hydrogen gas, or with a metal rather, is going to form hydrogen gas. With bases, there's really no general reaction with those. Electrolytes in solution, acids and bases are both electrolytes, which means they conduct electricity in solution. The stronger the acid or base is, the stronger the electrolyte it is going to be. Acids generally are going to start with H+. When we learned how to name acids, we always said they started with a hydrogen ion. That is the case. That's how you're going to be able to identify an acid. A base generally ends with hydroxide ion, with the OH. Acids, when you test an acid with litmus paper, it's going to turn litmus paper red. And when you test a base with litmus paper, it's going to turn it blue. Phenolphthalein is a very common indicator. An indicator is a substance that changes color in the presence of an acid or a base. So like litmus paper changes red in the presence of an acid and blue in the presence of a base. Phenolphthalein turns clear in the presence of an acid and turns hot pink in the presence of a base. And BTB is another indicator. It's called bromothymol blue. With acids, it will turn yellow. And if it's in a basic solution, it is going to turn blue. When we look at our lab, we will look at some different indicators. All right, so getting down into some properties, other properties of acids and bases. In a neutral solution, hydrogen and hydroxide are equal to each other. So that is true if you have a neutral solution. In an acidic solution, though, you have more hydrogen ion concentration than hydroxide. And in a basic solution, you're going to have more hydroxide ion concentration than hydrogen ion. An Arrhenius acid is defined as a compound that ionizes to yield hydrogen ion in solution. So it's saying when it dissociates, it's going to produce or give off that hydrogen ion in solution. A monoprotic acid yields one hydrogen ion, hence the prefix mono. A diprotic acid is going to give off two hydrogen ions, and a triprotic acid is going to give off three hydrogen ions. An Arrhenius base is defined as a compound that ionizes to yield the hydroxide ion in solution, which is, of course, OH negative. So in an Arrhenius acid-base reaction, your products are always going to be salt and water. And if you remember from when we looked at double replacement reactions back in January, hydrogen ion and your hydroxide ion make HOH, which of course is H2O. They combine to make water. So that's the water that we're seeing in the Arrhenius acid-base reaction. So in looking at our notes here, and I see that it got rid of my arrows, so I'm going to draw those in. We're going to predict the salt and water that is produced in the reaction. And the way we're going to do that is by looking at the ions that the acid and the base dissociate into. So for example, HCl, or hydrochloric acid, has a hydrogen ion and a chloride ion. Sodium hydroxide has a sodium ion and the hydroxide ion. Now, I mentioned earlier that water comes from your hydrogen and your hydroxide ion. So what you have left over is what's going to produce your salt, the sodium and the chloride ion. So that's where sodium chloride is coming from. And then part of what we would normally do with this is identify what is the acid, base, and salt in the solution. So HCl, since it starts with hydrogen, is going to be our acid. NaOH, since it ends with hydroxide, is going to be our base. Sodium chloride, of course, is our salt, and H2O is our water. So we're going to continue to predict products here and a couple more reactions. You're going to have to do that in your homework as well. And we're going to predict what the salt would look like. And then we're also going to identify what the acid, base, and salt are in the reaction. All right, so the first one we're looking at here, we have HF, which is hydrofluoric acid. So it starts with hydrogen, that makes it our acid. And we have lithium hydroxide, ends in OH, so that is our base. HF dissociates into H plus and F minus. Lithium hydroxide dissociates into Li plus and OH negative. Now your hydrogen and hydroxide ions have to match. Notice I have one hydrogen ion and one hydroxide. They are going to combine to produce one water molecule. You have the lithium and the fluoride, and those add up to 0. Plus 1 minus 1 adds up to 0, so you would just need one of each in your compound. Your salt is always aqueous. And here, you're also just producing one salt particle. And again, we would identify this as our salt there. In the next reaction, we have potassium hydroxide plus carbonic acid. Potassium hydroxide is going to be our base because it's ending with OH, and H2CO3 is going to be our acid because it starts with the hydrogen. Now, if we look at their dissociation, I have potassium and hydroxide, and with the carbonic acid, I have two hydrogens and carbonate, which is CO3, 2 negative. Now my acid, or my hydrogens and hydroxides, do not match. Notice I have two hydrogens and only one hydroxide. To get them to match, I have to put a coefficient of 2. That gives me 2 hydroxides, 2 hydrogens, which means I'm going to make 2 waters. The hydrogens and the hydroxides always match, and they make the equal amount of waters there. What I have left over then is potassium and carbonate. Now here, our charges do not add up to 0. When they did not add up to 0, we had to switch our charges. So we have K2CO3, potassium carbonate, and that is aqueous. And we are producing one of those. And again, we have just one carbonic acid then. In our last reaction we're going to look at, we have aluminum hydroxide reacting with sulfuric acid. Aluminum hydroxide is going to be our base because it's ending with OH, and H2SO4 is our acid because it begins with hydrogen. Now, if we look at how this dissociates, we have aluminum, which is Al3+, and we have 3 hydroxides. In H2SO4, I have 2 hydrogen ions and 1 sulfate. Again, my hydrogens and hydroxides do not match. They have to match in order to produce equal amounts of water. Because I have a 3 and a 2 for both of them, I'm going to have to make them both 6. So I end up with 2 aluminum hydroxides. That's going to make this 2 and that 6. And I'm going to put a 3 here to get 6 hydrogens, which would make this 3 sulfates then. So 6 hydroxides and 6 hydrogens combine to form 6 water molecules. The aluminum and then the sulfate, those charges do not add up to 0. Because they do not add up to 0, I have to switch them. What I end up with is 2 aluminums and 1 sulfate. And I just have 1 of those produced. And this is my salt. My ionic compound always ends up being my salt. All right, with the next type of reactions we're going to look at, you will see something called a hydronium ion produced. Now, if I have hydrogen, remember the most common form of hydrogen is atomic number 1, and it's going to have 1 proton, no electrons, okay? It has a mass of 1. So if we look at that, we would have the nucleus of the hydrogen atom has a proton, and it's got 1 electron to it. That's it. There's no neutrons to this atom. Well, when the hydrogen atom loses its only electron, so if we go and we erase that, eraser, all we're left with now is that proton. So when a hydrogen atom loses its only electrons, it's technically just a proton. So a proton is the same as the hydrogen ion. They are equivalent to each other. Now, when that hydrogen ion attaches itself to water, so here's our hydrogen ion, attaching itself to water, it makes something called H3O+. That is called the hydronium ion. The hydronium ion is what makes an acid an acid. That hydrogen ion attaching to the water is what makes a solution acidic. All right, so we're going to see that hydronium ion in action with these Bronsted-Lowry acid-base reactions. A Bronsted-Lowry acid is defined as a proton donor. Now, in the reaction below, we see that HX is turning into X minus. When it does that, it is donating or losing a hydrogen ion. Because HX is donating that hydrogen ion, it is identified as the acid in this reaction. Now, a Bronsted-Lowry base is known as a proton acceptor. Water, notice, turns into the hydronium ion. It is accepting an H+. It's accepting the hydrogen ion from HX. Because of that, water is our base in this reaction. It is a proton acceptor, which makes it the base. So let's do some more practice with this idea. Here we have a reaction. It says, in the forward reaction, the hydrogen ion or proton leaves water and combines with ammonia to make ammonia. So let's look at that. NH3 is turning into NH4 plus, and water is turning into hydroxide. Now, when water turns into hydroxide, it donated the hydrogen ion. Because water is donating there, water is going to be the acid. So water is the acid or proton donor. And ammonia is accepting the proton. It's going from NH3 to NH4 plus. So it's adding a hydrogen on. It's accepting one. Because it's accepting it, it is going to be our base. It is the proton acceptor. Now we could also look at this in the reverse direction. So in the reverse direction, we would be saying, okay, ammonium is turning into ammonia. And the reason we can do this in the reverse direction is because it's an equilibrium reaction. It's a reversible reaction. So when ammonium turns into ammonia, it is donating. So ammonium is the acid, and then hydroxide is accepting one to turn into water. So when you're going the opposite direction, now hydroxide's your acceptor. So hydroxide's your base. Because they are formed from ammonia and water, these guys are going to be called conjugate acid-base pairs. So hydroxide, we said, is our base. It's going to be our conjugate base. And ammonium, we said, was our acid. It's going to be called the conjugate acid. Now notice that the base turns into the opposite of what it was. The base is turning into your conjugate acid. And the acid is turning into the opposite of what it was. It is turning into your conjugate base. So we'll see that down here in some more practice problems. So a conjugate acid-base pair are two substances that differ from each other by a proton or a hydrogen ion. That's the only difference between them. So like ammonia and ammonium only differed by a hydrogen ion. Water and hydroxide only differed by a hydrogen ion. All right, so let's look at a couple of problems here and identify what the acid base and conjugate base are. The first thing you want to do is identify what the substance is turning into. HCO3 minus is turning into H2CO3. Now, when it does that, it is accepting a hydrogen ion. Since hydrogen carbonate is accepting a hydrogen ion, it is our base. That means what it's turning into is going to be the opposite of it. So that is going to be our conjugate acid. Now, if hydrogen carbonate is our base, that means water has to be our acid. And if you look at it, water turns into hydroxide, so it's donating a hydrogen ion. That would make it the acid. And it turns into the opposite of what it was, which is a conjugate base. All right, in the next reaction, we're going to start with HNO2. It turns into NO2 minus. When it does that, it is losing or donating a hydrogen ion. Because HNO2 is a proton or hydrogen ion donor, it now is our acid. It's going to turn into the opposite of what it was, which would make it a conjugate base. Since HNO2, nitrous acid, is our acid, water has to be our base. And notice it accepts a proton when it turns into the hydronium ion. Since water's our base, it turns into the opposite substance, which is the conjugate acid. really, if you can identify what one substance is, you can identify the three others. Now, in these reactions, notice that water is an acid in the first one, and it is a base in the second reaction. That's because water is amphoteric. It is a substance that can act as both an acid and a base. And so what is amphoteric in the above reactions? We just said this. It is water because it can act as both an acid and a base.